So it was the 3rd of September 1983 when I walked into the reception of BICC Telecommunications Cables Limited on the first day of my career. And on the wall hung a photograph. It depicted a dozen guys staring into a hole in the ground. Actually, it was more of a trench rather than a hole that was very, very long and very, very straight. At the bottom of the trench was just one guy who was busy installing something that looked rather like drain pipe. Just then, my boss arrived and he saw me looking somewhat bemusedly at the picture, and he said, to use a motorsport analogy, it's millimetric wave, guys. It's a drag racer. Fantastic straight line speed, but it doesn't take the corners well. It might have been the future shape of long-haul telecoms if it hadn't been for this. At that point, he handed me a sample of fibre optic cable. The cable comprised several plastic tubes stranded around a central strength member. Each one loosely contained a single optical fibre. He explained there were two types of fibre available. There was single mode and multi-mode. And to the human eye, they both looked pretty much the same. 125 microns diameter over the glass, coated with a layer of plastic that was 62.5 microns thick. They differed only in their respective core geometries. Single mode having a step index core of about 8 or 9 microns, and multi-mode a grade index core of about 50 microns. Now, despite single modes being lower in cost and far better in performance than multi-mode, and was recognized, as Tim mentioned, as the ultimate goal of things that we wanted to deploy. At that time, it wasn't being deployed at all. And fundamentally, that was because of issues around availability of optoelectronics, but at a more practical level, issues of splicing and connectorization. These required precise alignment. So a small offset in the order of microns might only have a small impact when connecting two multimode fibers together, but could yield an unacceptably high loss in the splicing of single mode. Now, over the next year or so, these issues were solved, and in '84, the first single mode systems were deployed. And although multimode is used extensively today in private enterprise networks and some data centers, since that time, single mode fiber has become, in one form or another at least, ubiquitous in the external networks of telecoms carriers. Now, in the second half of the decade, transmission rates increased at a fair pace from 140 megabits per second to 2.5 gig, and distances of 30 to 40 kilometers were achieved. However, a number of technologies emerged in the late 80s and early 90s that enabled a dramatic increase in the bandwidth-length product. And the two that I wanted to touch on are optical amplification and external modulation. Now, these, along with other techniques such as optical filtering and forward error correction, resulted in the ability to deploy high-capacity transmission systems which delivered a total bandwidth of 400 gigabits per second over distances of about 600 kilometers without any form of intermediate electronic regeneration, using a technique called dense wave division multiplexing. Now, there are few inventions that I think can be really described as being game-changing or creating a paradigm shift. But the optical amplifier, along with the invention of fiber and the semiconductor laser, really has to be up there with them. Its operating principle, which involves pumping an erbium-doped silica fiber at either 980 or 1480 nanometers, creates optical gain by creating an inverted population. Stimulated decay emitting a photon then occurs when incoming photons interact with the excited erbium ion. Now, the really cool thing about the ADVA is that the emitted photons adopt exactly the same wavelength, phase, and direction as the photons which initiate their release. This results in not only high gain, but as all the stimulated photons head off in the same direction, but also the ability to amplify multiple channels at the same time in the same piece of erbium fiber. This was absolutely fundamental to achieve DWDM transmission over long distances and fundamentally resulted in its widespread adoption ever since. The next enabler I want to talk about is external modulation. Now, initially, to superimpose a binary data stream onto an optical carrier was simply done by modulating the laser's bias current. And that works fine for short distance low bitrate interfaces. However, at data rates of 10 gig over any appreciable distance, the oscillations of frequency and amplitude which occur when the bias current is turned up conspires with the fiber's dispersion to distort the received eye, resulting in a performance impairment. Now, the solution to this came in the form of external modulation, which allows the laser to be left on continually and its output signal is then modulated in the optical domain. Now, there are two techniques which were developed for external modulation, but of them, the Mach-Zehnder interferometer was highly effective in generating a well-formed eye by creating a phase difference in the two arms that run through the modulator. It was, I suppose, to use the seldom used words of Craig Revel Horwood, judging the celebrity was on Strictly Come Dancing, it has truly excellent rise and fall. Now, Mach-Zehders were initially fabricated in lithium niobate. This led to excellent performance, but led to also quite large packaging sizes. But migrating to indium phosphide or silicon photonic processes presented opportunities for both size reduction and integration with other optical components, the value of which is going to become apparent later. Now, the other attractive thing of the Mach-Zehnder is that it's fairly agnostic to the wavelength of the laser to which it's connected, at least across the C-band. And this facilitated the use of tunable lasers, which emerged in the mid-2000s and became instantly popular. Now, tunables were initially marketed as enabling fancy new architectures, such as those in which the path an optical channel takes through the network can simply be determined by tuning its wavelength, which in reality was a capability that only was commercialized in more recent times. Its true value was in OPEX savings. And despite being more complex and more expensive than fixed wavelength lasers, they offered what we call a lower TCO, or total cost of ownership, by reducing the spares holding required to support the operation of DWDM systems, an issue that's become really acute as a number of channels have risen over time. Now, device technology is one part of the story, fiber performance is the other. And this slide shows a spectral attenuation profile of an early G652 standard single-mode fiber. The loss at 1300 nanometers is about 0.25 dB per kilometer compared to 0.2 at 1550, which shows why moving to 1550 was of interest for systems that were initially loss limited. However, back in the 80s, it was clear that as bit rates increased, sooner or later, the issue of dispersion has to be addressed. And one of the ways in which this was done was to develop a new single-mode fiber type called SMFDS, or dispersion shifted, which had a zero dispersion point at 1550, and it was standardized in ITU in a standard called G653. And at the time, it was adopted by a few operators, not many, and certainly not BT, as a way of overcoming the dispersion problem. However, when DWDM technology became available in the 90s, we discovered a somewhat deleterious effect when you multiplex a number of closely spaced channels together at reasonable power levels in a fiber that has no dispersion. The effect was called four-wave mixing, and it effectively prevented DWDM being used in this fiber type. However, for the operators that had deployed it, all was not lost, because when L-band DWDM occurred, which is a transmission at slightly higher wavelengths, the dispersion in that band was just sufficient to suppress the impacts of four-wave mixing, and so a usable workaround was created. Now, as we kind of edge forward into the beginning of this century, significant amount of effort has gone into driving the technology in three fundamental directions. One is continued increase of the capacity of the core. The second was increasing utilization of the DWDM aggregate, wavelength agility as we call it, by the introduction of optical add-drop multiplexing. And then finally, driving fiber optic networks closer to the edge. And of all of these things, the two that I really wanted to touch upon are the core technology using coherent transmission and the DWDM in the metro edge. Now, coherent transmission solved at a stroke all of the issues of dispersion and PMD that had challenged the deployment of 10 gig DWDM systems in the core. At the same time as massively increasing the transmission rate, it also enabled transmission distances from a few hundreds of kilometers to several thousands of kilometers to be achieved, and therefore further validating the strategies of those operators who decided to stick with G652 fiber from the outset. Now, a coherent transmitter fundamentally has, or coherent interface rather, fundamentally has two essential building blocks. There's the DSP, the digital signal processor, and the optical engine. So the DSP provides the interface to the line card, which takes digital electronic signals in and converts them into an analog format to be handed off to the optical engine. The optical engine comprises all of the optical components which enable a coherent transmission system to be realized. Now, over years, since 2010, when the first 100 gig coherent interface was introduced, the size and footprint of the technology has been scaled down quite significantly, partly down to Moore's law shrinking capacity of the DSP, partly down to integration of the photonic engine into a single photonic light guide circuit, a package called an IC Trozer. And this is a photograph of such a device, which uses silicon photonics. It incorporates all the components which are used in the optical engine apart from the laser, in a package size of about 15 mil by 22.5 by 3.6. A further benefit of coherent is the fact that the interface can be programmed, and for any given line rate, you could choose different modulation depths and a different baud rate. Going to fast baud rates enables transmission to be achieved in a larger bandwidth. Going down to modulation depths, we get a narrower passband, but slightly shorter transmission distance. So we have the ability to optimize the channel in order to fit the amount of bandwidth we have available for it. I'm going to skip over now just to talk a little bit about DWDM in the mobile edge, because I think it's quite an interesting area of transmission. As we push fiber out towards the edge, connectivity to mobile base stations has some fundamental requirements which need to be addressed. The first one, obviously, is fiber scarcity. The second one is uncontrolled temperature environments at cell sites, which causes a challenge for operation of DWDM systems. Then we have point-to-multipoint connectivity, and then finally increased latency sensitivity, which could come from evolutions of the RAM. So let me just skip through to the key slides. So this is a single fiber working solution which is currently being deployed for mobile backhaul. It features an Ethernet NID equipped with colored optics connected to a filter, which effectively enables single fiber working transmission to take place. Now, single fiber working is not new for the DWDM system. It's been around since the 1990s and was used in a number of instances where there was critical fiber exhaust. But why it's being used here is somewhat different. Going to single fiber working enables the upstream and downstream paths to be made more or less identical. And that's fundamentally important when it comes to delivering sync key and phase information over an Ethernet network. Now, another issue could be the building of point-to-multipoint networks. Most of the solutions we've deployed so far in mobile backhaul have been point-to-point. But to really exploit the capacity of the fiber, it may be necessary to build points-to-multipoint at some time, in other words, tree and branch networks. Now, that yields an interesting practical problem, because what it means is that the filter structure itself could not be co-located anymore with the Ethernet NID that it's connected to. So when the installer goes to to configure the Ethernet box, he may not know what wavelength he has to tune its laser to. The answer to that could come in the form of auto-tuning. In other words, transmitters and receivers which talk to each other using an out-of-band comms channel and enable themselves to find the right wavelength without any user intervention, which could result in a more plug-and-play type approach being taken to the deployment of optical networks. The final point I wanted to touch on was the impact of evolution in the mobile RAN. So today, DRAN is how we deploy mobile backhaul today. In the future, there could be a need to improve the user experience by pooling the BBU assets in a common location. That means taking them upstream of the cell sites. Now, to do that by extending the distance of the Fibre link, which is the link between the BBU and the remote radio unit, which currently exists in the cell site, yields a number of problems, not the least of which are latency and occupancy of the optical link. The current initiative with the NORAN is to come up with something called a split buy, which enables part of the DU to be located upstream. So now we have an intermediate location, and that FX link is now limited by latency. Now, as most of the latency of an optical link comes from either the electronics or the time of flight of an optical signal in a fibre, some of the techniques using hollow core that Neil talked about could really have an interesting impact in this part of the network and could change the way in which they're architected and laid out. So, in conclusion, I think the next 5 to 10 years will see fibre extending into the fixed and mobile networks at a rapid pace. To do that, continued innovation is going to be required to achieve the deployment at the required scale and at the required cost. And therefore, I think the optical communications industry is going to remain a really exciting place to be in, offering those who join it the opportunity to build on the innovations of the last 40 years. Thank you very much for your attention.